In this video lecture, we will go through the methods of preparation of colloidal solutions. Before this video lecture, we have understood what all types of colloidal solutions we have, right? And one important types of colloidal solutions that we have studied is your lyophilic salts or colloidal solutions, and the second is your lyophobic colloidal salts, right? Lyophilic, if you recall, are liquid loving, or that can easily mix up substances that can easily mix up with liquid or dispersion medium. They will form lyophilic colloidal solutions, right? Since they can easily mix up, right, with the dispersion medium, so the lyophilic colloidal solutions can be easily prepared, right? So we say that lyophilic salts can be prepared directly by mixing substances with dispersion medium, right? Because they are liquid loving, philic is loving, lyo is liquid. Since they are liquid loving or dispersion medium loving, they can easily form colloidal solutions, right? Example of such substances is your starch, starch, gelatin, right? Soaps, all these can easily form colloidal solutions since they can easily mix up with the dispersion medium, right? And the second type of colloidal solutions are your lyophobic colloidal solutions. If you remember, lyo is your liquid, phobic is means heating, right? So these are liquid heating or dispersion medium heating. So when we say dispersion medium heating, we mean that the substances will not easily mix up with the dispersion medium. Since they are dispersion medium heating, so they do not easily mix up with the dispersion medium, right? And so we say that lyophobic salts cannot be prepared directly, right? And the reason that these lyophilic can be prepared directly or easily, or why they mix up with the dispersion medium easily, is because their particles, the particles of starch, gelatin, soaps fall in the colloidal range, right? And we know that colloidal range is your 10 to the power of minus 9 to 10 to the power of minus 6 meter, or 1 nanometer to 1000 nanometer, right? Since the particle size in case of lyophilic salts fall in colloidal range, so they easily or directly form colloidal solutions. Whereas if we talk about lyophobic colloidal solutions, the particles, right, but the particles of these substances do not fall in the colloidal range. The particles are either bigger, right, like that of suspensions, right, or they are smaller. So when the particles are bigger, we need to disintegrate or break them into smaller particles so that they fall in this range of colloidal size particles. And when the particle size are smaller, then we have to employ, the smaller particles need to associate or aggregate to form particles of colloidal range, right? So now in the rest of the lecture, we will concentrate more on lyophobic colloidal solutions, and we will see how the substances that do not easily form colloidal solutions, what methods we can employ so that we can change the particle size of those substances, like those of metals and metal sulfides. If you remember, they do not easily form colloidal solutions. So what methods we can employ so that we can change the particle size of those substances to the colloidal size particles, right? So these are the methods. If the particle size is bigger, right, then we have to break or disintegrate those particles into the particles of colloidal range, right? So the methods that we will use or employ to break the bigger particles into smaller particles, we will discuss those particles, right? We call them as dispersion or disintegration methods. Since we are disintegrating bigger particles to smaller particles, we call them as disintegration methods. The first is, so what ways we can employ? If we break the particles using a machine, right, we call it a mechanical method or mechanical disintegration method, right? And if we are using electricity to break bigger particles to smaller particles, we call it as electrodisintegration method, because we are using electricity to break bigger particles into smaller particles, so we call it as electrodisintegration method. The first method, mechanical disintegration, where we will use a machine right? The machine that we would be using is the colloidal mill, right? Colloidal mill is because this mill is used to convert or to disintegrate bigger particles into particles of colloidal range. That is why we call it colloidal mill or colloid mill, right? So let's just quickly see. This is the design of colloidal mill, that consists of these two steel discs, right? These two steel discs can rotate in opposite directions at a very high speed of around 70,000 revolutions per minute, right? And you can see that there is a gap between these two steel discs, right? And then there is a hollow shaft. From the top of this hollow shaft, we will suspend the solution of this suspension, right? And since this suspension, we know the particle size of suspensions are bigger than those of colloidal particles. So this colloidal mill will disintegrate the particles of suspension, which are bigger particles, into smaller particles. So what we will do is we will pour the solution of this suspension in water from this hollow shaft, from the top of this colloidal mill, right? And then we will start rotating, right? Then we'll rotate this colloidal mill. The steel discs of this colloidal mill will rotate at a very high speed, right? So when this will rotate, the suspension which is here in this red part that you see will break into smaller particles of colloidal size, right? So from this we can easily prepare particles of colloidal size using colloidal mill. The second is your Redix Art Method. In this we are using electricity, so we call it a electro disintegration method. Using electricity, we are breaking bigger particles into smaller one, right? If you look at this arrangement, it consists of this ice bath, right, which is ice cold, since it has ice inside it. Then you have another container that has a dispersion medium in it, right? And in this dispersion medium, there is an electric arc between the metal rods. These metal rods are also immersed in this dispersion medium, and then you have an electric arc between these metal rods, right? And the metal rods, right, using these method first. Using this Redix Art Method, we generally prepare colloidal solutions of metals like gold, silver, platinum, right? So if we want to prepare colloidal sol or colloidal solution of gold, then these metal rods would be that of gold. If we are preparing colloidal solution of platinum, then we will take these metal rods of platinum. So depending on what colloidal solution you need, of what substance colloidal solution you need, accordingly you will take the metal rods, right? So when you struck the electric arc, right, between these metals, right, so when you struck the electric arc between these metal rods, it will produce intense heat, right? Due to the intense heat produced, right, the metal will vaporize, right? Due to the intense heat produced from this electric arc, these the metals in this metal rods will vaporize, right? And when the metal which is vaporized, when that metal will come in contact with this ice cold, right, solution which is outside this container which has dispersion medium, it will immediately condense, right? And when it will condense, it will change into particles of colloidal size, right? So this is quite easy. It just involves vaporization of metal followed by condensation, right? So it will immediately in the ice cold water bath, resulting in the formation of particles of colloidal size. This is your ice cold water bath, right? So when the metal which is vaporized due to intense heat produced from this electric arc, when the vaporized metal will come in contact with this ice cold bath, it will condense into particles of colloidal size, right? So these metals which were initially not in the range of colloidal particles, right? Initially these metal rods was not in the range of the particles of colloidal size, which is 10 to the power of minus 9 to minus 6 meter, right? So after this, after we employed this Redix Art method, we get particles of colloidal size, right, of the metal, for whichever metal you want to prepare the colloidal solution, right? So I'll quickly repeat. When we struck the electric arc, the metal will vaporize, right? So when the vapors of the metal will come in contact with this ice cold bath, it will condense, right? So when it will condense, it will change into particles of colloidal size, right? So this is how you get particles of colloidal size, and you can prepare the colloidal solution of the respective metal, whichever metal you have taken as the metal rods, right? So using this method, you can prepare colloidal solutions of platinum, gold, right? Using Redix Art method, you can prepare the colloidal solution of these metals, right? So you may get a question like what method you can employ to get colloidal solution of platinum, silver, right, or gold, right? So you can if they want this disintegration method, right, just remember that if you want to prepare the gold sol or platinum sol using disintegration method, you employ Redix Art method, right? So using Redix Art method, you can prepare the gold, the sols or the colloids or the colloidal solution of metals like platinum and gold, right? And then this also we have discussed colloidal mill, right? That will again disintegrate bigger particles into smaller using this mechanical way or the machine, right? Then we have another important way wherein we can prepare particles of colloidal size, right? This is your peptization method, right? In peptization method, generally what we do is we take freshly prepared precipitate. We know that precipitate is of bigger size, right? Then using this peptization method, we will break that precipitate into particles of smaller size of that colloidal range, right? So what we do is we generally take freshly prepared precipitate, right? Because it is easy to it is easy to prepare particles of, or it is easy to disintegrate, right, freshly prepared precipitate to obtain the colloidal size particles, right? So in this peptization method, what we do is we take freshly prepared precipitate, right? Then we will employ a method to break, right, this particles of precipitate into colloidal range, right? The most common example of this is when you prepare the colloidal solution of ferric hydroxide, right? So what you do is, in this method, when you convert a precipitate into that of colloidal size particles, right, what you do is you employ or you use a suitable electrolyte, right? That electrolyte will convert this precipitate into smaller particles of colloidal size, right? So process of converting fresh precipitate into colloidal particles by shaking it with dispersion medium and a suitable electrolyte. That suitable electrolyte is known as peptizing agent, right? So this method is known as peptization method, right? I'll just quickly again, what we do is we take the freshly prepared precipitate, right? For example, let's take this precipitate, right, and we have taken this precipitate in dispersion medium, right? Dispersion medium. And to this, we will shake the precipitate with dispersion medium and with a suitable electrolyte. We will see what this suitable means. Suitable electrolyte, right? So when you shake the freshly prepared precipitate with the dispersion medium and the suitable electrolyte, this precipitate will break into particles of colloidal range, right? So this precipitate will break into particles of colloidal range. Now let's take example. You can prepare the colloidal solution or the colloidal particles. You can break the precipitate of ferric hydroxide into particles of colloidal range, right, by shaking it with the dispersion medium and the ferric chloride solution. Electrolyte here is ferric chloride, right? So what you do is you take this, let's say this is your FeOH3, right? So when you to this freshly prepared precipitate of ferric hydroxide, right, you add this small quantity of ferric chloride solution, right? If to this precipitate you add small quantity of ferric chloride solution, here this ferric chloride solution is acting as an electrolyte, right? Then this precipitate will break or dissociate into smaller particles of colloidal range, right? These are particles of ferric hydroxide, right? This is what it means, right? So how does this happen? We need to understand that also. I'll repeat. We take a precipitate, right, freshly prepared precipitate, and then we shake this precipitate with the dispersion medium, and then we add a suitable electrolyte to it, right? When you add a suitable electrolyte to this precipitate, it will dissociate into smaller particles of colloidal range, right? Now let's see the reason why this freshly prepared precipitate will dissociate into smaller particles. What happens is, in this suitable electrolyte or the electrolyte that we have added, this contains ferric ions plus chloride ions, right? What this FeOH3 will do, this FeOH3, will absorb these ferric ions, right? It will absorb these ferric ions, right? And if you just look at the formula of ferric hydroxide, it also has ferric ions, right? So when it will absorb ions, a similar ion, right, then there is electrostatic repulsion due to similar ions between ferric ions of ferric chloride and ferric ions of the precipitate ferric hydroxide. There is electrostatic repulsion between the two ferric ions, right, which will result into, due to this electrostatic repulsion, this precipitate will dissociate into smaller particles of colloidal range, right? So what we say is, this precipitate will absorb the common ion from the added electrolyte, which will result into electrostatic repulsion, and due to this electrostatic repulsion, the bigger particles will dissociate into the smaller ones, right? This is what it means. I'll repeat, this is actually important. Peptization method is used to convert freshly prepared precipitate into particles of colloidal range. What we do is, we take the freshly prepared precipitate and then we shake the precipitate with the dispersion medium, and then we'll add a suitable electrolyte. Here the suitable electrolyte will contain a common ion with that of your precipitate, right? So when you add this electrolyte, a common ion would be absorbed by this precipitate. So when this precipitate will adsorb the common ion formed from the added electrolyte, which is your peptizing agent. There it will result into the adsorption of this common ion by this precipitate will result into electrostatic repulsion. So due to this electrostatic repulsion, this precipitate will disintegrate into particles of smaller size, right? And the smaller size would fall in the range of colloidal solutions or colloidal particles, right? So I hope this is clear, right? So ferric hydroxide is an example, is the common example for which you can prepare the colloidal solution, right, or the particles of colloidal solution using this Peptization method. The other example is your precipitate of silver iodide, right? If you have a precipitate of, say, silver iodide, what you can do is the suitable electrolyte that you can add to convert this silver iodide into particles of colloidal range should contain either silver ion or iodide ion. So you can take either silver nitrate or you can take silver nitrate, or you can take potassium iodide, right? Potassium iodide contains this iodide ion, so it will adsorb the iodide ion, and that will result into electrostatic repulsion and will break this precipitate into smaller one. Or if you take silver nitrate contains this common ion silver. If it will adsorb this silver ion, right, then this will result into electrostatic repulsion in this silver iodide, which will result into disintegration of precipitate into the particles of colloidal range, right? So the electrolyte that we are adding, remember we call it a peptizing agent, right? So suitable electrolyte is your peptizing agent, and suitable electrolyte, by suitable we mean it should contain a common ion, right, with that of your precipitate, right? Now we'll come on to the other methods where smaller particles which may or may not be of colloidal range will associate to form bigger particles of colloidal range, right? So associated particles should fall in the colloidal range, which is this range, right? So here the first method is the chemical reaction will do a chemical reaction, like here this As2O3, when hydrogen sulfide is passed through the solution of this oxide, it will change into colloidal solution of sulfide, of its sulfide, right? So here when hydrogen sulfide is passed through arsenious oxide, solution of arsenious oxide, it will change into colloidal solution of arsenious sulfide. This is arsenious oxide, solution of arsenious oxide. When hydrogen sulfide is passed through it, it will change into arsenious sulfide, right, which falls into colloidal particle size. Then is your reduction method, right? So using reduction method, again you can prepare colloidal solutions of gold, silver, platinum, right? Now this is here also we can prepare using Redix Art Method. Also we have seen how we can prepare the colloidal solution of gold, silver, platinum. Now using this aggregation method, we need to employ this reduction reaction so as to prepare the colloidal solution of gold, silver and platinum. So what we will do is we can obtain the colloidal solution or the colloidal sol particle of gold using this gold chloride, right? This is the solution of what we do is we take a suitable reducing agent, which is tin chloride here, and then we'll react it with the chloride of the metal for which you want to prepare the colloidal solution, right? So gold, silver, platinum can be obtained by reduction of their dilute solution of their salts, chloride salts, with the suitable reducing agent. Here reducing agent is tin chloride. It's simple reaction, you get this gold of colloidal range, gold particles of colloidal range, right? Then you have another method where you can use hydrazine. NH2 is your hydrazine, or formaldehyde. when this hydrazine or formaldehyde is reacted with gold chloride, it will again change into gold of colloidal range, right? The other is your oxidation method, where you can prepare this sulfur sol, right? Sulfur sol or sulfur colloidal solution can be obtained when hydrogen sulfide is bubbled through the solution of an oxidizing agent. Oxidizing agent is your bromine water, or we take it as nitric acid, right? So when nitric acid or bromine water, right, through nitric acid or bromine water you pass this hydrogen sulfide gas, it will change into sulfur sol, right? It will change into colloidal sulfur, right? So hydrogen sulfide, let me just quickly write down the chemical equation. So hydrogen sulfide H2S will react with bromine to form HBr plus sulfur, right? Same is with the other oxidizing agent, which is your nitric acid, right? So when hydrogen sulfide is passed through bromine water, which is your oxidizing agent, it will form this sulfur plus HBr, right? So this is the way to prepare sulfur sol, right? So if you get in your exam how to prepare sulfur sol, you can mention this directly, that when hydrogen sulfide is passed through this bromine water, you get sulfur sol, right? So the other way is when you shake it with the nitric acid, right? When hydrogen sulfide is passed through nitric acid plus HNO3, you get NO2 plus water, NO2 plus water plus sulfur, right? Here also you obtain this sulfur sol. So this is how you can obtain sulfur sol when hydrogen sulfide is passed through oxidizing agents like bromine water or nitric acid. Third, the other way is your hydrolysis, right? When ferric chloride, right, is shaken with water, it will change into ferric hydroxide, which is your colloidal solution. It will fall into colloidal range, right? So ferric hydroxide and aluminium hydroxides are obtained by boiling solutions of their corresponding chlorides, right? So here you have taken these chlorides and you are boiling the chlorides with chloride with the warm water. So you prepare the sol of ferric chloride. Similarly, by boiling aluminium chloride with warm water, you get aluminium hydroxide. By solvent exchange method, right, using the solvent exchange method, you can prepare sulfur and phosphorus and fairly soluble. Okay, the sulfur and phosphorus, this is using the solvent exchange method, you can prepare the salts of sulfur and phosphorus. So what you will do is, sulfur and phosphorus are fairly soluble in alcohol, less soluble in water and fairly soluble in alcohol. So what you do is, you take sulfur or phosphorus, you dissolve it in alcohol, and then you dissolve this solution of sulfur or phosphorus in alcohol. You add this solution to water, right? So when you add this, you take sulfur, right, you dissolve it in alcohol, right, and then you add this solution of sulfur in alcohol to water, right? So this is when you add this to water, you get sulfur sol, right? Or same as this, you get phosphorus sol, right? If their alcoholic solutions are poured in water, this is the alcoholic solution of sulfur or phosphorus, right? When this is poured in water, you get sulfur sol or phosphorus sol. Colloidal solutions are obtained of sulfur or phosphorus. The other is by condensing vapors of substance into the solvent. Colloidal solutions of sulfur and phosphorus are obtained by passing their vapors in cold water. Similarly, if you have sulfur or phosphorus in vapor state, if you pass the vapors of sulfur or phosphorus through cold water, vapors will condense and form colloidal solutions of sulfur or phosphorus. The other is by excessive cooling.